What if a transformer could carry a private plan while it writes? This page introduces the free transformer, a decoder-style model that conditions generation on hidden variables learned without labels. Those latent variables are inferred through a variational learning procedure, so the model discovers useful internal structure on its own. The payoff is practical. By letting the generator lean on a compact, learned summary of high-level factors before producing tokens, the model can capture richer patterns and deliver sizable gains on downstream tasks. How did one architecture become the backbone of modern AI? Since 2017, transformers, especially the decoder-only design popularized by GPT, have powered language, code, and multimodal systems by predicting the next token from the previous ones. Their simplicity and effectiveness made them the default choice for generative modeling. Yet, after years of engineering progress, the fundamental recipe remains the same: pure autoregression. This work revisits that assumption. The idea is to let the model form a higher-level internal summary before emitting tokens, enabling distributions that are more natural and expressive than a step-by-step next token-only view. The core change is to augment a decoder transformer with latent variables and train it as a conditional variational autoencoder. Conceptually, the model first infers a compact, hidden description of what it is about to say, then conditions token generation on that description. Variational inference provides a way to learn those hidden variables without supervision, and the proposed implementation adds only a small compute and memory overhead to a standard decoder. Does this actually help? The method is validated by training 1.5B and 8B parameter models from scratch and evaluating them on multiple downstream benchmarks. The reported results show consistent improvements, indicating that the latent conditioning translates into practical performance gains. What do decoder transformers really model? They approximate the probability of a sequence by predicting each token given all the previous ones. At generation time, they sample one token after another, each step recalculating the distribution for the next symbol conditioned on the history so far. Crucially, all the model's choices live at the token level. There is no separate sampled plan or style variable guiding the sequence. Any higher-level intent is only implicit in the shifting probabilities over tokens as the sequence unfolds. Consider generating movie reviews with clear positive and negative categories. A standard decoder can learn both styles and will produce them correctly given enough data and capacity. But it never explicitly decides, this review is positive or this one is negative up front. Instead, that intent emerges implicitly as it emits words and adjusts the next token probabilities based on what it has already written. The chain rule guarantees that any distribution can, in principle, be modeled autoregressively. However, implicit representation is not always the most efficient or controllable. Introducing explicit latent decisions can make the structure more direct, improving learning and generation for tasks with clear underlying factors. When a hidden cause really drives the data, ignoring it forces the autoregressive model to do a lot of extra work. Modeling the full system with that hidden variable can actually be simpler than trying to explain everything token by token. Consider a latent coin flip that lands heads or tails with equal chance. Each observed bit is just a noisy copy of that coin. Most of the time it matches, but with a small probability, it gets flipped. That's a clean, intuitive data generation story. Given the coin, the observed bits are independent. In other words, once you know the hidden cause, predicting the next bit doesn't require sifting through the entire past. Conditioned on the coin, the next bit probability is straightforward. It mainly follows the coin, with a simple adjustment for the noise rate. The prediction rule is short and easy because the latent variable captures the shared structure. Drop the coin and try to go purely autoregressive, and the conditional suddenly depends on all previous bits in a complicated way. You're forced to integrate over what the coin might have been, which turns a simple rule into a cumbersome history-dependent calculation. That messy expression says, to predict the next bit without the latent coin, the model must infer the coin's value from the entire history. In practice, it acts like a running estimate that weighs how many ones and zeros you've seen and how reliable they are under the noise. This introduces combinatorial terms and makes the dependency on sequence length explicit and brittle. It gets worse when the latent is a position, like where a pattern starts in a sequence. Then the model must constantly carry a belief about, is the target here yet? And small estimation errors accumulate. Those errors are hard to avoid and can derail generation. Bottom line, a purely autoregressive approach can become needlessly complex, error-prone, and ill-suited to data whose natural description involves hidden structure. This forces the model to spend capacity on reconstructing hidden causes after the fact, rather than using them directly. A few mistaken tokens can send the inference off course, compounding errors. High-level concepts don't emerge up front. They're pieced together post hoc to fit the data, which is fragile, especially out of distribution. Our goal is to fix this by letting the model condition its autoregressive process on its own latent random variables, ones it chooses and samples, rather than only on what is explicitly present in the training tokens. Think back to generating movie reviews. Instead of guessing sentiment from the words already produced, the model can first sample a single yes-no latent for sentiment, and then generate all tokens conditioned on that choice. This removes the need for a complicated posterior guess during generation and makes the process cleaner and more controllable. We can implement such latents by computing each one from what's already known, past tokens and earlier latents, plus a fresh draw of randomness. Conceptually, you supply a random seed at each step and let the network transform it, together with the context, into the next latent. The seed provides variability. The function encodes dependency on history. If we provide enough independent random seeds during generation, training can shape a rich hierarchy of latents with whatever dependency structure the task needs. The only limits are model capacity and how much context it can carry. Just as picking the next token uses logits plus a random draw, an internal activation that mixes learned signals with randomness is a deliberate choice the model makes while generating. Because these choices depend on private random draws, they aren't fully recoverable from the output tokens. The tokens reveal only partial information about the latent decisions. What changes when you slip a global random state into a decoder? The diagram contrasts three setups. First, a plain decoder. Transformer generates tokens step by step using only past tokens. Next, a conditional VAE version augments this with a latent variable z and an encoder that infers z from the full sequence, so the decoder can condition on z while generating. Finally, the free transformer injects z midway through the stack and, during training, reuses the first half of the decoder plus a single non-causal layer to act as the encoder. The key idea: keep the benefits of a meaningful z while minimizing extra compute at training time and keeping inference as cheap as a standard decoder. The figure walks through the evolution from a standard decoder to a conditional VAE, then to the free transformer. In the VAE, an encoder proposes a distribution over Z given the sequence, letting the decoder generate the same sequence when conditioned on samples of Z. The free transformer achieves the same effect with much less overhead by injecting Z in the middle of the stack and constructing a lightweight training time encoder from the decoder's first half plus one non-causal layer. The payoff is a controllable latent state with minimal training time cost and no extra cost at inference. Want a global knob for style or structure at generation time? You simply sample a latent Z from its prior and then run the usual left-to-right decoding, but every step's probabilities are nudged by Z. That way, Z consistently steers the entire sequence without changing the basic autoregressive mechanics. Training is trickier. We want the model to assign high probability to the observed sequence, accounting for all the possible latent choices that could explain it. That means averaging over Z, which is intractable to compute exactly, so we need a smart way to infer likely Z values during training. Conceptually, the sequence's probability is the average of the decoder's likelihood across all plausible latent states, weighted by how likely each Z is under the prior. This marginal likelihood rewards models that can explain the data under reasonable latence rather than memorizing specific Zs. To estimate that average, we need samples of Z that are consistent with the sequence, i.e., an approximation to the posterior over Z given S. Finding those latents is the hard part and motivates introducing an encoder that proposes Z values tailored to each sequence. Enter the VAE encoder. It learns a distribution over Z given the sequence so that when we sample from it and condition the decoder on that Z, the decoder is likely to regenerate the sequence. This is an approximate inference mechanism, tractable, learned, and good enough to guide the decoder. We jointly train the decoder and this encoder so they co-adapt. The encoder proposes useful latents, and the decoder learns to use them. At first, Z is just noise. With training, it organizes into meaningful factors. For a movie review model, the encoder may implicitly map a review to a region of Z corresponding to positive or negative sentiment. Different parts of Z-space then act like specialized generators, one for positive reviews, another for negative, raising the likelihood of the observed data. A critical design choice is to cap how much information the encoder can smuggle into Z. Without a bottleneck, the encoder could simply copy the whole sequence into Z, letting a trivial decoder appear perfect in training but useless at inference when no encoder is available. The VAE objective addresses this by penalizing the information in Z via the KL divergence between the encoder's proposal and the prior. Combined with the reconstruction term, it forms a trade-off. Use enough information in Z to faithfully reconstruct the sequence, but keep Z close to the prior, so it carries only the essentials. This prevents cheating and encourages Z to capture broad, reusable structure rather than verbatim details.
We are Genapad. Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genapad.com.
Where do the latent variables actually plug into a decoder-only transformer? This diagram answers that by showing a split-stack design with a lightweight encoder used only for training and a causal decoder that does the actual generation. Starting from the bottom, token embeddings for the prefix flow through the first half of the causal transformer blocks. In parallel, a non-causal, bidirectional encoder looks across the entire sequence during training to infer latent structure that the prefix alone can't reveal. The encoder's readout is converted into a set of discrete binary choices via a binary mapper, then packaged as a sparse 2H-channel 1-hot representation Z. A small post-sampler projection turns Z into a signal that can be injected back into the model midway through the stack. From there, the top half of the causal decoder continues processing, and the final readout produces next token logits. Conceptually, the lower decoder layers capture local context, the encoder proposes global latent cues, and the mid-stack injection lets those cues steer the upper decoder layers before prediction. The KV arrows indicate where keys and values can be cached or pre-filled for efficiency. The tensor shapes simply indicate that everything is computed per time step t, with model width d, vocabulary size v, and latent width h. This caption clarifies how the free transformer is run and why it's efficient. The orange components belong to the encoder path and are evaluated only during training or when pre-filling the KV cache. They are skipped during normal generation. Elements with dashed borders don't add parameters. The binary mapper, detailed later, turns encoder signals into discrete binary latents, which are represented as a 2H-dimensional 1-hot structure Z. At inference time, the encoder is not used at all. Z is sampled from a simple uniform prior, so generation remains as fast as a standard decoder while still benefiting from learned latent structure. Note, normalization and residuals are omitted in the diagram for clarity. Ever wonder what a decoder transformer actually does at runtime? It takes your input tokens, turns them into vectors, then passes those vectors through a stack of identical processing blocks. Each block mixes information across positions with self-attention and refines it with a small feed-forward network, all stabilized by normalization and residual connections, so signals and gradients flow cleanly. At the end, a final normalization and a linear layer convert the processed vectors into scores for every possible next token. Those scores drive the next token decisions during generation. The training objective is the usual cross-entropy, which simply asks, how much probability did the model assign to the correct next token? Minimizing it teaches the model to place higher probability mass on the right continuations, aligning learning with accurate next token prediction. What's inside a transformer block? Two key pieces. Multi-head self-attention, which lets each position selectively read from others, and a token-wise MLP that reshapes information at each position. Residual connections wrap these parts so the model can add new computations without forgetting earlier ones, and normalization keeps the scale of activation stable. Together, these ingredients stack to build rich, long-range representations. The clever twist of the free transformer is where it injects noise Z, right in the middle of the stack. By doing so, the lower half of the decoder can be reused by the encoder during training, so only one extra non-causal block and a couple of linear layers are needed on the encoder side. This keeps overhead minimal while still giving the model a global latent handle that can steer the upper layers. Place Z too early, and the encoder won't have enough capacity to infer meaningful latents. Place it too late, and the decoder won't have enough depth left to use those latents effectively. Mid-stack strikes a practical balance. Before anything clever happens, the model turns each token into a vector with a fixed width, one vector per time step. This puts the sequence into a continuous space where attention and MLPs can operate. Midway through the stack, the model pauses to introduce a latent code for each position, a one-hot choice among C categories. During generation, these choices are sampled uniformly from a simple prior, adding controlled randomness. During training, and when pre-filling caches with a known prefix, an encoder proposes latents that are consistent with the observed tokens, so the latents learn to reflect structure in the data rather than pure noise. How does this latent actually steer the network? The one-hot codes are first mapped into vectors, aligned with the model's hidden width. Then, at the next block, the current sequence features make their queries as usual, but the keys and values are nudged by adding the latent-derived vectors. This biases attention toward patterns suggested by the latent choices, letting the upper half of the decoder integrate these global hints. The remaining blocks refine the result, and a final linear readout turns it into token logits over the vocabulary. Who decides the latent codes during training? The encoder does. It samples Z to match the observed sequence, ensuring the latent variables explain the data well. The same mechanism applies when priming generation with a fixed prefix and pre-filling the key value cache. The encoder proposes latents compatible with that prefix. The encoder includes a dedicated non-causal block that can see the entire sequence at once. This full context view is important because the decoder's conditioning can create long-range dependencies. To infer good latents, the encoder must account for effects that span the whole sequence, not just the past. An unusual but purposeful choice. The encoder queries come from a learned constant vector repeated across time, while the keys and values come from the decoder's lower half features. By not feeding token identities into the queries, the encoder is discouraged from memorizing token-wise mappings and is nudged toward capturing global properties that transfer across examples and tasks. What does the encoder produce for each position? A compact vector of small dimension, here 16. This low-dimensional summary is lightweight to compute and easy to regularize, and it provides just enough capacity to parameterize how categorical latent choices should be made downstream. What actually happens during a forward pass when we add latents to a decoder? First, the tokens are embedded and processed by the lower half of the decoder blocks to build a strong contextual representation. During training or the initial prefill phase, an auxiliary encoder peeks at this representation and proposes a global latent summary. That proposal is turned into a discrete choice via the binary mapper, but training still gets gradients through this step using a straight-through trick. At inference time, the encoder is skipped and the latent is simply sampled from a uniform prior, keeping generation as fast as a standard decoder. The chosen latent is then projected into a vector and injected mid-stack, so the first upper block and the remaining blocks steer their computations with this global signal on top of the token-wise context. Finally, a readout layer converts the resulting hidden states into logits for the next token distribution. How do many tiny binary decisions become one powerful global switch? The encoder produces logits that define independent probabilities for H binary bits. Those bits are sampled to form a single integer from 0 to 2*h-1, then encoded as a 2*h-dimensional one-hot vector, for example, 65, 536 options when h equals 16. A straight-through gradient lets the model learn through this discrete step as if it were continuous. Think of Z as a per-token categorical latent. Each token picks one of 2*h codes, represented by a one-hot vector. For generation, the prior is uniform over all codes, so there's no bias toward any particular latent. During training, the encoder defines a proposal distribution over those codes based on the entire sequence. The KL term then measures how much the encoder's proposal deviates from uniform, penalizing overly confident or skewed proposals unless the data truly needs them. With a uniform prior, the KL reduces to a simple idea. It is large when the encoder's distribution is sharp, low entropy, and small when it spreads mass more evenly, high entropy. In practice, this term controls how much information the latents are allowed to carry and prevents them from becoming either trivial or overly dominant. How do we stop the latents from collapsing to something useless? We add their KL cost to the loss, but apply a token-wise free bits rule. Each token gets a small KL budget that doesn't incur a penalty. Only the KL above a threshold contributes to the loss, encouraging the model to use the latent capacity without being punished for modest, useful information. The training objective is the usual next token cross-entropy plus a regularizer that charges only for excess KL beyond the free bits allowance. Concretely, the KL term is clipped below the threshold and averaged across time. This means the model pays nothing for the first few bits of information per token, but is gently pushed to justify any additional complexity in the latent choices. The threshold is a tunable hyperparameter that sets how many bits per token are free. Picture the encoder writing a short binary code for each position. Its final linear layer emits H logits per token, one for each bit, which we interpret as unnormalized evidence for that bit being 0 or 1. The binary mapper samples each bit independently from these probabilities. Independence keeps the mechanism simple and efficient, while the combination of bits still spans a large, expressive, discrete space. A sigmoid turns each logit into a Bernoulli probability. During training, a straight-through estimator lets gradients flow through these discrete samples, so the encoder learns which codes are helpful. Once the H bits are sampled, they define a unique index among two ℏ possibilities. We then produce a one-hot vector at that index, giving the model a crisp, discrete latent that can steer the upper decoder layers. This mapping from bits to the one-hot position is deterministic. Pick the bits, and the category is fixed. That makes the latent both interpretable and easy to inject into the network. How do you let gradients flow through a discrete choice? The trick here is to represent each latent category D by an H-bit binary code. For each time step t, the encoder predicts H-independent Bernoulli probabilities, 1 per bit. From these, the model builds a score for every possible code. The log probability that the predicted bits exactly match the code for D. This gives a smooth, differentiable score for each discrete option, even though the eventual choice is hard and one-hot. Conceptually, the score G for category D is just the log likelihood of that specific H-bit pattern under the encoder's bitwise sigmoids. You add up per-bit contributions. If a bit in the code is 1, you take the log of the predicted probability for 1. If it's 0, you take the log of the probability for 0. Summing over bits yields a single number per category. These scores let the model rank categories and, crucially, provide gradients to the underlying sigmoids that produce them. What does the binary mapper actually output? In the forward pass, it picks a hard, one-hot category based on the scores, but in the backward pass, it treats those scores as the pathway for gradients. That way, the model enjoys crisp decisions at inference while still learning which bits to nudge during training. The detach operator means use this value in the forward pass, but stop gradients here. It keeps the hard choice intact for generation, while preventing it from blocking the learning signal that flows through the smooth scores. Putting it together, the output blends a hard, one-hot selection with detached scores so that the forward behavior stays discrete Yet the gradients track what would have happened if we had used the soft scores. This is a straight-through style estimator tailored to a binary-coded categorical latent. Why encode a k-way latent with h-binary bits instead of predicting k-logits directly? Because the sigmoid is monotonic, small changes in a bit's logit have predictable effects on that bit's probability, which makes gradients cleaner and learning more stable. It is also far more parameter efficient and encourages compositional structure. The model learns H reusable switches instead of two *H separate categories. The experiments unfold in 3 steps. First, a controlled synthetic task probes whether the model actually uses its latent Z and what it chooses to store there. Next, the method is compared against strong decoder-only baselines at the 1.5B and 8B scale under different KL/free bit settings to understand the accuracy control trade-offs. Finally, a larger 8B model trained on 1T tokens tests whether the gains persist at scale. Can we catch the model leaning on Z? A tiny synthetic world makes that visible. By training small free transformers under different free bits thresholds, we can see how much information the encoder decides to pack into Z as the KL budget grows, from nothing to a few global facts to too much. Here's the recipe for building each synthetic sequence designed to isolate global attributes like which letter and where it appears. Start with 64 underscores. Choose a random uppercase letter and a random position. Then insert a block of 8 copies of that letter at that position. Add noise by flipping any character to an exclamation mark with small probability, 1/16. Finally, prepend a short prompt that includes the chosen letter, cueing the model about the target. The result is a mostly blank sequence with a single global motif, which letter appears and where. Figure 3 would show sample strings, a sea of underscores, a contiguous 8-letter island somewhere inside, and occasional exclamation marks as noise. Visually, it's clear which global factors matter, letter identity and position, and that's exactly what a good latent should capture. Training 4 models with increasing free bits thresholds, K reveals how Z is used. To diagnose control, all models receive the same random prompt and produce 3 groups of outputs. In the blue group, each sequence gets its own independently sampled Z. In the green groups, many sequences share the same Z. If sharing Z makes outputs align on global traits, that's evidence the latent is steering generation. What happens as the KL budget grows? With a very small KL, the model behaves like a plain decoder. Z is ignored, and outputs vary idiosyncratically. As the budget increases, the model first stores the target's position in Z, so shared Z forces the island to appear in the same place, a bit more KL, and it also records the noise pattern, synchronizing the exclamation marks across shared Z samples. Push the budget too far, and the encoder memorizes the entire sequence, so generation degenerates. The decoder over-relies on Z and stops properly responding to the prompt. The sweet spot is where Z captures just the salient global structure, not the full target string. For fair comparison on standard benchmarks, the baselines are strong decoder-only transformers implemented in the same metafair transformer codebase used in prior work. This keeps architecture, training stack, and evaluation consistent, isolating the effect of the latent variable upgrade. At first glance, these strings look like a jumble of letters and exclamation marks. So what's the pattern? Each row is a fixed-length sequence where, at a random position, a single letter is repeated to form a visible target block like KKKK or CCCC. Everywhere else, the sequence is filled with exclamation marks as pure noise. A brief prompt at the start tells you which letter to expect, but not where it will appear. Visually, the figure makes the global structure obvious. Identity of the letter varies, its position shifts, and the background remains noisy, giving the model little local help without a good global summary. Why design a dataset like this? Because it isolates the exact global factors a latent should capture. The prompt reveals the target letter, but the model must still find where that block sits and ignore the distracting noise. This cleanly separates three pieces of information: letter identity, given, target position, hidden, and random noise, irrelevant. That makes it straightforward to test whether the latent Z learns the useful global cues, position, and noise without resorting to memorizing the entire sequence. What does the latent actually store as we allow it more capacity? By increasing the free bits threshold, we let the model spend a larger KL budget. With almost no KL usage, the model behaves like a plain decoder. Z carries nothing helpful. Give it a little room, and Z first locks onto the most valuable global cue, the position of the target block. Increase capacity further, and Z also records the noise pattern, which improves generation. Push it too far, though, and Z tries to encode the entire sequence. That overfits. It works when the encoder is present during training, but at inference, Z is sampled from a simple prior, so it no longer matches the true sequence and generation becomes wrong. The colored boxes in the figure indicate regions used to probe Z by sampling different latents, revealing which global attributes are being encoded at each capacity level. What kind of base models are we upgrading? The experiments build on strong, modern decoder transformers. They use components that are now standard for performance and stability: SWIGLU activations for efficient nonlinearities, RMS norm in a pre-norm setup to keep training well-behaved, rotary positional embeddings to encode token order without fixed position vectors, and grouped query attention to speed up attention with minimal quality loss. The vocabulary is large, on the order of hundreds of thousands of tokens, which makes the modeling challenge realistic and competitive. There are two model scales. The smaller is a 1.5B parameter model with 28 layers. It ties the input embedding and output projection weights, which saves parameters and often improves generalization. Its attention uses 12 query heads, but only 2 key value heads, a GQA-style setup, trimming memory, and compute. It was trained on roughly 47 B tokens using about 32 H100 GPUs for around half a day. The larger is an 8B model patterned after Llama -3 to 32 layers, a wider hidden size, 32 query heads, and 8 key value heads. It was trained on a much bigger corpus, about 200 B tokens with 256 H100s in roughly a day, or up to 1 trillion tokens in several days. Together, these choices give a fair testbed across medium and large scales without exotic tricks. How much extra cost does the free transformer add? Very little. Compared to the baseline decoder, it needs a small encoder only during training and slightly more KV cache activity. In practice, that translated to roughly a 3.6% overhead for the 1.5B model and about 3.1% for the 8B model. At inference time, the encoder is skipped and the cost remains essentially that of the original decoder. To keep the comparison clean, the authors deliberately avoided other sources of improvement. The goal was to isolate the effect of the latent variable upgrade rather than mix it with unrelated training tricks. They kept the exact same architecture optimizer and learning rate schedule as the baselines and did not hyperparameter tune for the new setup. They also resisted common variational autoencoder shortcuts, such as turning off sampling at inference. Instead, they followed the textbook objective and procedure. One design choice was to fix H to 16 bits for the discrete latent code, which yields 536 possible latent categories, comfortably in the same ballpark as a large token vocabulary. This makes the latent space expressive without being unwieldy. It's worth emphasizing that the baseline's optimization settings were highly tuned for a pure decoder. A system that combines an encoder and a decoder may benefit from different schedules or regularization. So these results are conservative. Targeted tuning could plausibly improve them further. Before scaling up, they probed how the free transformer behaves and how to set the free bits per kiloliter threshold K. Think of K as a budget of information the latent variables are allowed to carry per token. Too low and latents can't help. Too high and they might leak target information. Training was stable across K values. Cross-entropy fell smoothly without unusual spikes, similar to baselines. The KL term quickly dropped below the target K and stayed there, showing the regularizer effectively constrained the latent channel. As K increased, cross-entropy improved slightly, as expected when the model is allowed to use more latent information, but the gains were tiny, on the order of hundredths of a nat. In short, more KL helps a bit, but you don't need much to see the benefit. Where is the danger zone? Allowing K equals 2 nats per token, about 4 bits, caused the training loss to plummet for both model sizes, but downstream performance collapsed. That's a telltale sign the encoder learned to smuggle too much information about the next token into the latent, making training look great while harming generalization. By contrast, smaller budgets, for example around 2 bits per token or less, did not collapse, which aligns with the fact that the baseline 8B model's entropy during training is still higher than that smaller budget. There isn't enough room for the latent to cheat. Detailed results for the 1.5B and 8B models across 4K settings, from roughly half a bit to 2 bits per token, are reported in tables 1 and 2, with training curves in the appendix. The tables show how the trade-off plays out across tasks as K changes. What improved the most? Reasoning-heavy benchmarks. The free transformer gave substantial gains on Human Eval Plus, MBPP, and GSM-8K, which rely on multi-step reasoning or program synthesis. The 8B model also saw clear improvements on multiple-choice sets like MMLU and CSQA when given a small KL budget, about half a bit per token. This pattern fits the intuition that a compact global latent can steer the model toward consistent plans or solution structures without overfitting. Where do a few latent bits help the most? In these 1.5B parameter models trained on 47B tokens, the biggest wins show up on generative reasoning tasks. Human Eval Plus and MBPP both jump noticeably when the model gets a small latent budget, roughly up to 1 bit, and GSM-8K also improves, peaking around 1 bit. That pattern fits the intuition. A global latent can steer high-level plan and style, which matters a lot for code and step-by-step math. On multi-choice knowledge and common sense, results are mixed, but mostly near parity. HelloSwag and PIQA hover around baseline. CSQA bounces around baseline with small dips in some settings, while OBQA sees clear gains at higher budgets. Arc Challenge shows a small uptick at one setting, but is otherwise flat to slightly down. Arc Easy is essentially unchanged. For text understanding, Race is mostly flat to slightly down, but BoolQ benefits at moderate budgets. Open domain QA-NQ TQA trends slightly down with latents here. Overall, small latent budgets give consistent benefits on generation-heavy tasks with neutral to mixed effects on knowledge lookup and reading comprehension. More bits do not automatically help. The sweet spot tends to be around a fraction of a bit to 1 bit. This table summarizes 1.5B models trained on 47B tokens under a training recipe tuned for the baseline and left unchanged for the free transformer. That makes the comparison conservative. The free transformer wasn't hyperparameter optimized here. Despite that, it only adds about 3.6% compute and parameters for its encoder, a modest overhead for the observed gains on generative tasks. The cited appendix figure tracks how these differences emerge over the course of training. Do the gains survive at larger scale? At 8B parameters trained on 200B tokens, the story is similar but more sensitive to the latent budget. Generative code and math see consistent boosts. Human Eval Plus improves the most around a half bit. MBPP peaks at a quarter bit. GSM 8K improves notably around 1 bit. Common sense and knowledge benchmarks are mixed and depend on the budget. MMLU and CSQA can swing from drops at low or high budgets to sizable gains around a half bit. HeliSwag and PIQA are effectively unchanged, with tiny improvements at some settings. When a grande tends to dip slightly, for RC, the challenge set shows small improvements at certain budgets, often 2 bits, while the easy set stays near parity. Text understanding is stable to slightly worse. Race high edges up at a quarter bit, but race middle drifts down. Bool Q performs worse across budgets here. Open domain QA-NQ TQA stays near parity, with small ups and downs depending on the budget. The pattern echoes the smaller model. Global latents most reliably help tasks that require planning and structured generation, and the best budget is modest. Too little or too much can negate the gains. This table covers 8B models trained on 200B tokens, with the training setup tuned for the baseline and reused as is for the free transformer. The free variant adds roughly 3.1% compute and parameters for its encoder, keeping the cost increase small. The referenced appendix figure plots the training curves, showing how performance evolves as training progresses under these fixed settings. What happens when you give a large decoder a small, latent steering signal? This table reports how 8B parameter models trained on 1T tokens perform when upgraded to the free transformer with a tiny latent budget, about half a bit per token, compared against a standard baseline. It shows both the final checkpoint and an average over the last third of training to smooth out training noise. Where does the latent upgrade help most? The clearest wins are on generation-heavy and reasoning tasks. Coding and math benchmarks improve. Human Eval Plus rises from about 0.268 to 0.299, MBPP nudges up, and GSM 8K gains around a point. These are the kinds of tasks where a global plan or style can guide many tokens at once, so a small latent signal pays off. For multiple choice general knowledge, the picture is mixed, but positive overall. MMLU and Common Sense QA see solid jumps, roughly plus 3 to 4 points for MMLU and plus 4 points for CSQA, suggesting latents help with global context or strategy in multi-step reasoning. HeliSwag is essentially unchanged, and PIQA ticks up slightly. A few benchmarks dip a little. Winagrand, OBQA, and ARC Challenge drop slightly, and ARC Easy loses about a point. Text understanding benchmarks are mostly flat. Race High drops a bit, Race Middle is steady, and Bool Q shows a small gain. Open Domain QA, that leans on factual lookup, NQ-TQA, edges down slightly. Averaging over the last third of training tells the same story. Improvements persist on the reasoning and coding side, while knowledge retrieval and some common sense tasks remain neutral or slightly negative. In short, tiny global latents seem to steer structured generation and reasoning more than they improve pure recall or shallow comprehension. Why report both the final number and an average over late training? Performance can wiggle from checkpoint to checkpoint, so averaging the last third gives a steadier estimate of relative gains. Importantly, optimization hyperparameters were tuned for the baseline and then reused unchanged for the free transformer. The free transformer adds a lightweight encoder only during training, increasing compute and parameters by about 3.1% for that phase. Inference cost stays the same. Training curves illustrating these trends are provided in Appendix C. What happens when you scale training to 1 trillion tokens? We trained 8 B-parameter models on 1 T tokens, a setup much closer to real-world deployments. Both the plain decoder and the free transformer get substantially stronger, letting us test whether the latent upgrade still adds value when everything else improves. To keep the latent budget modest, we set the KL target to about half a bit per token, a choice that worked best at 200 B tokens. This provides a gentle, global steering signal without letting the latents overfit by memorizing details. How should we read the results? Table 3 reports 2 views, the final checkpoint and the average over the last third of training. Figure 7 shows the curves are roughly steady over that window, so averaging reduces checkpoint noise and gives a more reliable picture of true performance. Do the gains survive at scale? Yes, scores rise on coding and math-style generation, human evil, MBPP, GSM-8K, and also improve on knowledge and reasoning multiple choice, MMLU, CSQA. Other benchmarks look steadier, with fewer dips, matching the trends seen at smaller training budgets. Many efforts combine VAEs with decoder transformers to add global control over content or topics, while keeping fluent token-by-token generation. Optimus pairs a BERT encoder with a GPT-2 decoder, trained with a variational objective. BERT compresses the whole input into a latent summary, and GPT-2 conditions its generation on that summary. Practically, the latent comes from a special classification token that summarizes the sequence. GPT-2 is then nudged by either appending this summary as an extra token at each layer or by adding it to token embeddings. To prevent the model from ignoring the latent KL collapse, training uses a free bit strategy that enforces a minimum information flow before penalizing. This setup improves controllable text generation with GPT-2 and helps BERT generalize better to low-resource languages, highlighting the value of a learned global code. Building on this, Z et al. Add auxiliary objectives, such as predicting a story's topic using external labels to shape the latent space. These extra targets make the latent dimensions more interpretable and easier to guide. Fang et al. S-conditional VAE uses 2 pre-trained GPT-2 models, a non-causal encoder that reads the full text to produce a sequence representation averaged into a latent, and a causal decoder conditioned on that latent. They try several injection points, adding the latent to input embeddings, attaching it to attention keys and values, or adding it before the softmax, and show they can steer outputs without harming fluency. ADAVAE follows a similar 2GPT-2 design, but extracts the latent with a modified attention readout. It feeds this code into the decoder either through the attention pathway by concatenating to keys and values, or by biasing the final logits, mirroring what worked in Optimus and CVAE. Think of the free transformer as a standard decoder with a compact VAE built in. A single non-causal block infers a global summary during training, adding only a few % overhead in compute and memory. Because it learns latents unsupervised and conditions generation on them, the model can plan globally while decoding locally. Conceptually, it plays a role similar to chain of thought, providing structure that guides next token decisions, but it does so inside a learned latent space rather than via longer text and reinforcement learning. Combining the two could merge internal planning with explicit reasoning traces. Why is it exciting when a model improves without any hyperparameter tuning? Because it hints that the architecture itself has a better inductive bias, built-in assumptions that match the structure of real tasks. Seeing gains across different benchmarks and model sizes suggests the effect is robust, not a quirk of training settings. In short, the upgrade seems to make transformers reason in a more naturally helpful way. Training curves look bumpy, and a likely culprit is the tug-of-war between the encoder and decoder being optimized at the same time. As the encoder shifts how it proposes latents, the decoder's target effectively moves, and vice versa. Stabilizing this dance might require different optimizers, learning rates, schedules, or alternating updates. There's also flexibility in how the latent signal is embedded. The current choice is just one option. Alternative embeddings or injection strategies could change what information the latents carry and how reliably the upper layers use it. What happens when we scale up both parameters and data? The benefits might grow, plateau, or morph, and the best latent budget could shift. Careful scaling studies will reveal whether the same recipe holds or whether regularization and design choices need to evolve.